Welcome to Study Room for Computer Science. In my today's video lecture, I would like to discuss analysis of selection sort. Before moving on to the analysis part, I would like to demonstrate how this selection sort works by simply taking a suitable example. Then after that, I will move on to the analysis part. So I am simply taking the example sum 4, 0, 1, 2, 8 and 3. Okay, and its index is 0, 1, 2, 3, 4 and 5. Then I am taking one more variable called min, and in that variable I am storing the index of the first number. Okay, then I will explain the idea of selection sort. In the variable min, I will store the index of first number, and this selection sort sorts the number in ascending order. If I am sorting in the ascending order, the smallest number always should appear in the list first. Okay, so the basic idea is that I will simply compare this 4 with the second number. Then if the second number is smaller than the first number, then I will simply update the value of min as 1. Here I am simply comparing 4 and 0. 0 is less than 4, so I will simply update the value of min as 1. Okay, now the minimum element is 0. Then I will compare the 0 with the 1. Now the 0 is the minimum number. Then 0 with the 2. Then 0 with the 8. Then 0 with the 3. Now 0 is the smallest element in the given list. Okay, then I will exchange this 0 with the first element. Now the list of elements becomes 0, 4, 1, 2, 8, 3. This is the pass 1 of selection sort. This is the pass 1 of the selection sort. After the pass 1, the smallest element will be in its exact position. So in my previous video, I have explained what is called bubble sort. In bubble sort, after the first pass, the biggest number will be in its exact position if I am sorting it in an ascending order. Okay, now I will go with the pass 2. Now this 0 is in its sorted position, and I need to sort the remaining set of numbers 4, 1, 2, 8 and 3. Okay, now I will store the minimum values, min values. What is the index of the starting number? 1. Now I will store 1. Then I will compare 4 with 1. When I am comparing this 4 with 1, 1 is less than 4, so I will simply update the min as 2, because 2 is the index of 1. Then I will compare this 1 with 2. 1 is smaller element. Then I will compare 1 with 8. 1 is the smaller element. Then I will compare the 1 with 3. 1 itself is the smaller element. So 1 is the second smallest element in the entire list, or 1 is the smallest element in the this list starting from 4 to 3. Now I will simply exchange this 4 and 1. Here I have exchanged this 4 and 0. Here I am simply exchanging this 4 and 1. Here 4 is the starting element. Okay, now the list becomes 0, 1, 4, 2, 8, 3. This is the result after pass 2. Okay, so these elements 0 and 1 is in its sorted position. Now we need to sort the remaining set of elements. Okay, so now the value of min is nothing but 2, because the index of 4 is nothing but 2. So this is 2. Then I will simply compare this 4 and 2. When I am comparing this 4 and 2, I can see that 2 is the smallest element. Okay, then for 2 is smaller than 4. Then what is the index of 2? Index of 2 is nothing but 3. I am simply changing it as 3. Now I will compare 2 with the 8. 2 is the smaller element. Then I will compare 2 with 3. Then again 2 is the smaller element. Okay, so I will simply exchange this 2 with the 4. Okay, then I am exchanging this 2 with the 4. What is the current list? 0, 1, 2, 4, 8 and 3. Now this is the sorted list 0, 1 and 2. This is the result after pass 3. Okay, now we need to sort the elements 4, 8 and 3. 4 is the starting element in the remaining list. What is the index of 4? The index of 4 is nothing but 3. So I will store the minimum element as 3. Now 0, 1, 2. Okay. Then I will compare 4 and 8. 4 is the smaller element itself. Then I am comparing this 4 and 3. 3 is smaller than 4. So now what is the value of index? This 3 will be changed to 5. Okay. Then I will exchange this fifth element with the fourth element. What will happen? This 3 and 4 will get exchanged. Now 3 will become here, 8 and 4 will come here. Okay, now this is the pass 4. Okay. Now this 0, 1, 2, 3 is in its sorted position. Okay. Then I will start with the remaining list. This is the first element. So what is the index? Index is nothing but 4. Okay. Now I will compare this 8 with 4. 4 is the smallest element. When 4 is the smallest element, and there are no more elements in the list, so you can simply swap this 4 and 8. So what will be the 0, 1, 2, 3, 4 and 8. So this is the pass 5. Okay. So you can see that similar to bubble sort, if we have an n elements, we need to perform n minus 1 passes, because here we have 6 elements. We have gone through pass 1, pass 2, pass 3, pass 4 and pass 5, gone through 5 passes. Okay. So if we have a n number of elements in the list, we need to go through n minus 1 passes to sort the entire list by using selection sort. Okay. Now let us discuss the analysis of selection sort. Okay. So let us take the previous example itself. Okay. In my previous video, we have discussed the bubble sort and its analysis. And when we are analyzing a sorting algorithm, we needed to take two things into consideration. That is nothing but comparison and swapping. These are the two basic operations involved in almost all sorting algorithms. Okay. So here also I am taking both the number of comparison and swapping for analyzing the selection sort. So let us see what is the number of comparison and swapping involved in each and every pass. We have already seen that we have n elements. We will be having n minus 1 number of passes. Here we have 6 elements. We will be having 5 number of passes. Okay, I am generalizing here. We have n elements. We will be having n minus 1 number of passes. Okay, assume that this is the number of elements. N is nothing but 6. Okay, what is the total number of comparison? We will assume first element as the minimum element. Then we will compare with each and every element. So we will be having n minus 1 number of comparison if we have n elements. So number of comparison is nothing but n minus 1. How many number of swapping will be there? First of all, we will assume the first element as the smallest element. Then we will traverse the entire array. Then we will find the index of the smallest element in the entire list. Then we will swap that element with the first element, which means that each and every pass at most one swap will occur. If the first element is the smallest element itself, the number of swap will be 0 in each and every pass. So we can have at most one number of pass will be there. Okay. Then in the next pass number 2, we will be having n minus 2 number of elements. If we have an we will be having n minus 1 number of elements. If we have, because the first element or smallest element will be in its exact position after the first pass. So we will be having n minus 1 number of elements. We will be having n minus 2 number of comparison. The number of swapping will be same. Then we will take the second element as the smallest element. Then we will traverse the entire list. Then find the index of the smallest element. Then we will swap that elements. Okay. So in each and every pass, the number of swap will be 1. Okay. That I can conclude. Okay. Then n minus 1, n minus 2. The next will be n minus 3. Then finally I will get 1. So the total number of comparison involved is nothing but 1 plus 2 plus 3 plus etc. up to n minus 1. That is nothing but sum of first n minus 1 natural numbers, n into n minus 1 by 2. So this is nothing but n square minus n by 2. Asymptotically you can return it as big of n square. Okay. Then what is the total number of swaps? Total number of swap is nothing but 1 plus 2 plus 3 plus etc. up to n minus 1. We will be having n minus 1 passes. So at most you can have n minus 1 number of swappings, because there may be a swap or may not be a swap in each and every passes. Okay, when you will be having a swap, at most one swap in each and every passes. What is the input combination? Suppose you are giving some elements 5, 4, 3, 2, 1. Because already sorted array, and if you want to sort an array in an ascending order and it is given in descending order, what will be the case? We will assume that this is the smallest value. but this is not the one. Then we will traverse the array, we will see that 1 is the smallest, then we need to swap the element, then the number of swap will be 1. Then we will assume 4 as the smallest element, then we will find it as 2 as the next second smallest element, then we will swap. Okay, so we will be having at most n minus 1 swaps if we are giving an array in a reverse order. Okay, if we are giving an array in a reverse order, that will be the worst case for this selection sort. Then when will be the best case? If we are giving in this case also the number of comparison will be the same. We will be having n into n minus 1 by 2 number of comparison. Then if we are giving some array as 1, 2, 3, 4, 5, what will be the number of comparison? We will assume that this has the smallest element, then we will compare each and every element, and we will find that the first element itself is the smallest element. So the number of comparison will be same and the number of swap will be 0 in this case. So I can conclude the total number of comparison involved in selection sort is nothing but n into n minus 1 by 2. Number of swaps, at most you can have n minus 1 number of swaps when an array is in reverse order, which means that you need to sort the array in an ascending order and it is given in a descending order, or vice versa. And best case occurs when an array is already given in a sorted order. If you want to sort in an ascending order, the element itself is given is in an ascending order, and vice versa. Okay, so in that case you will be you will be having n into n minus 1 by 2 number of comparison and a 0 number of swap will be there. Okay, and finally we can check whether it is a stable sort or an in-place sort. Selection sort is both a stable and an in-place sort. Stable sort is means that it always keeps the relative ordering of numbers. You can see my video comparison of sorting algorithms. You will get a clear idea of what is stable sort and in-place sort. And in-place sort is nothing but it does not require any extra space. So selection sort is as a stable sort and an in-place sort. Okay, and its complexity is nothing but big of n square, because in every case, whether it is an average case or a best case or a worst case, always the number of comparison is big of n square.
This is the conclusion for analysis of selection sort. For an n size input, we will be having n minus 1 passes to sort the entire array by using selection sort. The complexity is always big of n square, whether it is best case, worst case or an average case. The number of comparison is n into n minus 1 by 2. Number of swap equal to at most n minus 1, because we have n minus 1 passes. In each pass we will be having either 1 swap or 0 swap. Okay, best case occurs if an array is already sorted order, which means that if you want to sort an array in an ascending order and it is already given in an ascending order, or if you want to sort an array in a descending order and it already given in a descending order, that will be the best case for selection sort. In this case, the number of comparison will be n into n minus 1 by 2 and number of swap equal to 0. Worst case occurs when an array is already sorted but in a reverse order, which means that if you want to sort an array in an ascending order and it is given in descending order, and vice versa. In that case, the number of comparison is n into n minus 1 by 2 and number of swap is n minus 1. If you like this video, please share the video maximum and also subscribe my channel Study Room for Computer Science. Thank you.